Good day, everyone. I'm Hélène Bérard, the Director of the Statistical Geomatics Center at Statistics Canada. It is with great pleasure that I welcome you to this session organized by the Joint Task Team on Earth Observation for Agricultural Statistics. This task team operates under the guidance of two United Nations Committee of Experts. During this session today, our speaker will discuss how Earth observation data can be used to address specific questions, such as disaster assessment and the production of agricultural statistics. Please note that the question period will take place at the end of the session. I wish you all a great session. Thank you.
All right, we'll be moving on to our next speaker. Our next speaker is going to be Ms. Claire Bourrian. Claire is working with us she's joining us currently from the USA. She's a PhD, Senior Geographica at the US Department of Agriculture. Just a few more minutes and we're going to be sharing that right away.
Program.
I don't know, Claire, if you would like to say
statistical arm of USDA, and in recent years, we have responded to many agricultural disaster inquiries in the United States. And these have included hurricanes, regional flooding, derechos, fire, and in recent years, drought and extreme heat events. In this presentation, I'm going to describe some of our flood analysis methodology and how we're updating that using Google Earth Engine. Also, I'll describe the analysis we conduct for wind, drought, heat, and fire events, and then provide a summary. So agricultural disaster monitoring and assessment are important for food security, emergency assistance, crop insurance, agricultural statistics, which is what we do, and decision support. So the NASS disaster mapping team has been tasked with monitoring agricultural disasters in near real time and providing quantitative assessments of affected agricultural land using remotely sensed data and geospatial techniques. And this is all to support NASA's mission, which is to provide timely, accurate, and useful statistics in service to U.S. agriculture. To identify what cropland is impacted, we use our cropland data layer. The cropland data layer is an annually produced, georeferenced 30-meter crop-specific land cover data set, captures planted acres. It is freely available and open to the public, and we have been producing it at the national scale since 2008. And the 2021 CDL will be released in February of 2022. And I have the website for where you can access the cropland data layers. It's called Cropland Cross. And now I'm going to describe how we conduct inundation analysis. This has been a problem in the United States. We've been having very heavy rains in the springs, and that have prevented planting of crops. And so we're conducting this type of analysis more and more often recently. And we are using synthetic aperture radar currently, Sentinel-1. This is freely available data from the Copernicus program in the European Union. And we've been conducting this type of analysis since this has been available. And why are we using synthetic aperture radar? It's because it can penetrate through clouds, which is extremely helpful during hurricane events. And what I'm showing you here is on the left is an optical image where you can see this very heavy cloud cover. And in the center is a Sentinel-1 synthetic aperture radar image where there is useful information, and you can see the extent of water in these images. So the Sentinel-1 data, there are two sensors. It's a C-band synthetic aperture radar. We are using software provided by the European Space Agency, and the data is freely available for download within 24 hours of acquisition on the ESA site. Very, very useful. I've got a picture here just showing kind of the examples of flooding. This was during Hurricane Florence in September 2018. And this is the link to the Copernicus site. After we conduct pre-processing of the data and some log transformation, we use a manual thresholding technique is commonly used for this type of an application in which we separate water from other land cover categories in the log transform Sentinel-1 images. The low values would be water and the higher values would be other categories. This is just an illustration of that. The top left illustration is a Sentinel-1 image before the flood. Again, the dark shade is water, the light shade is other categories. We create a very simple, straightforward classification of water and other. And then in the bottom figures, we've got the after the flood event Sentinel-1 image, and on the right is the classification of that. So you can see how there's much more water after the event. And this was Hurricane Florence, September 2018. And then we did conduct an image differencing, and what we've highlighted here is that in red is where there's change. That's what we're looking for. And then we intersect that with our cropland data layer to identify what is cropland. And what we've got here on the right is the inundated cropland is red and regular cropland is in green. And the output of this type of analysis would be some maps. This is over quite a large area, Virginia, North Carolina, and South Carolina. And we've identified, fields that have been flooded in North Carolina and South Carolina and provided quantitative assessments of that impact. We have, in recent years, recently transitioned to using Google Earth Engine. The previous steps, was fairly time consuming. We were processing our own data, downloading it and processing it in the Snap toolbox. But this new method using Google Earth Engine proves to be much more timely and cost effective. It's really a similar analysis. It's just that the data is pre-processed and posted to Google Earth Engine. The cropland data layer is there as well. We identify, the dates that would be before the event and the dates after the event and the year of the cropland data layer we'd like to use. And we can get the same type of information out of Google Earth Engine. Different colors, but that's not really so important. What we're seeing here is, in this example, inundated cropland is in green. But it's the same type of analysis, just much faster. You can do much larger areas than we could by processing our own data. And this is an example for Hurricane Laura in August 2020. This is an example of a map that would be an output product of that analysis. Again, with those quantitative assessments of the impact of that flooding. And this was over 3 states, Arkansas, Louisiana, and Mississippi. We've also responded to wind events. This is an example of one of those wind events. This was a derecho that took place in Iowa, which is a very large corn and soybean production state in the United States. This happened in August 2020. We used NOAA, or National Oceanic and Atmospheric Administration data with estimated peak and wind gust information and Storm Prediction Center wind and storm reports. And we could identify the extent of, for example, corn and soybeans that were impacted by this derecho. And just in the last year, we conducted drought analysis using our new web application, Cropcasma. In the Western United States, last summer, there was some extreme drought and heat conditions. It was going on for quite a long time in July and August of 2021. We used soil moisture data, subsoil moisture, 9-kilometer subsoil anomaly data, and categorical data. And this is all hosted in Cropcasma, which is our crop condition and soil moisture analytics web application. And we conducted thresholding using that information to see what would be considered very dry or very abnormal conditions. And this is the example, the output from that analysis. This is showing drought and extreme heat report for the Western United States. This is actually Washington State, Oregon, and Idaho. And the very dark, brown colors are showing areas that have experienced very extremely dry conditions. And then you can determine the amount of cropland that are at these different levels. There have also been fires in the Western United States, quite a lot of fires that we've conducted. This is just an example of a fire that took place in Washington State in September 2020. It was the Cold Springs Canyon and Pearl Hill fires. And with this type of analysis, there would be a tabulation of how much cropland was within that fire perimeter. The data that would be used is the fire perimeter polygons provided by CAL FIRE and the USDA Forest Service active fire detection points, and also MODIS optical data for digitizing. And this map shows an example of those fires and the fire perimeter. We've used the cropland data layer, again, intersecting within that fire perimeter to see what types of crops would be impacted. And as far as we do disseminate our data via our website, our disaster analysis website. And on this website, we provide public access to maps, like I've shown you in this presentation, quantitative assessment reports of non-confidential data. We will use our previous year's information, crop information, to be included on there. Internally, we can use the within season. We post our geospatial data, metadata, which describes exactly the data that's used for the analysis, and a methodology paper. And at the bottom here is a link to our disaster monitoring website. And these are just some maps that would be posted to that website. The center picture shows there was extensive flooding in Missouri in May and June of 2019. And what you're seeing in red there is inundated cropland. And on the right is another one of those hurricane wind events showing the impact of these winds during Hurricane Irma in 2017. So in summary, we do monitor agricultural disasters in near real time and provide quantitative assessments to support crop estimation, decision support, and emergency response. And this capacity is possible due to the freely available and timely geospatial data, imagery, and software. And our geospatial products, maps, and assessments are delivered to NASS stakeholders and to the USDA Emergency Operations Division. And our non-confidential data are made available to the general public on the NASS Disaster Analysis website. There are ways to learn more. I've included the Cropland Cross link, our disaster monitoring website link, and a video on Google Earth Engine. Thank you.
Thank you, Claire, for that presentation. I'd like to open the floor to anybody who has any questions, and Claire is joining us for any response on those questions. Please, we'll be giving that around a good 5 minutes.
All right, so would you like me to speak and read the question?
Yes, please, you can.
All right, so it says here, how do you verify the classification based on the satellite is correct? Do you use VHR, aerial images, field check, or is SAR known to be very accurate for detecting water bodies? SAR is quite accurate at water bodies. However, now the classification as far as the cropland data layer, we do extensive accuracy assessments on that, just so you know. And then the SAR data, yes, we are, we don't go back and check each time. It's just quite accurate. This really is just an estimate of that. So hold on for a second. Was there any conversation internally around putting the USDA base map data on Google Earth Engine? vis-a-vis security issues or the other compliance. So the crop data layer is considered publicly available. Do you have any comments on this that other NSOs hesitant to use public cloud services could benefit from? Again, the cropland data layer does not identify specific farmers or anything like that. It is a 30-meter resolution, which for us is about 0.22 of an acre. It is considered publicly available. It is released after the growing season. Okay, is the cropland information based on surveys or on aerial imagery? We use satellite imagery, Landsat 8. We will use Landsat 9 this year as well. Sentinel-2 data. We actually use some list data as well. And then for our training data, we use internal administrative data. Do you want me to keep answering a few more? I don't know. How about time? I'll just answer a few more. You let me know when to stop. Would you please share the code of Google Earth Engine for performing the inundation analysis? Yes, there is some very excellent publicly available training. There's something called the NASA Applied Remote Sensing Training. NASA Applied Remote Sensing Training that has, and I can put a link, that has flooding, which is great. What method of classification was used in the SAR data? Any form of accuracy for classification determined. For the flooding, initially, when we
Claire,
we have a methodology paper, we did do an accuracy assessment, but we don't do it each time. There just is not enough time. Again, I'm going to put in the chat information about the NASA Applied Remote Sensing Training for flooding. Thank you all for the wonderful questions.
All right, we're going to be moving on to Gordon's videos. Gordon, you are with us, I believe, correct? You can just answer me via the chat because I haven't given you permission. I'll do that right away. That's for future.
Greetings to everyone. My name is Gordon Reichert, and I am the Senior Scientific Advisor for Remote Sensing and Geospatial Analysis within the Agriculture Division at Statistics Canada. Today's presentation will be on the crop yield model used at StatCan for producing yield estimates for the July and September occasion of the crop reporting series. Throughout the presentation, I will give a very brief overview of agriculture in Canada. As well, I will present the background on the motivation, objective, and partnerships as part of establishing and running the yield model. I will discuss the 3 data sets used in the model and the results of the yield model during the drought year of 2021. Lastly, there will be a summary and a way forward component to the presentation. Canada's population is slightly more than 38.4 million people. Total land mass is approximately 9.1 million square kilometers, with total farmland representing about 7.1% of the total landmass. There are 10 provinces and 3 territories and 69 census agricultural regions, which are the lowest level of aggregation used in the yield model. To the right of the slide is a map of Canada with the boundaries of the provinces and territories and the 69 census ag regions superimposed on the agricultural area delineated in green. Let's begin with the motivation. The purpose of the field crop surveys is to obtain information on seeded and harvested field crop areas, average yields, production, and on-farm stocks at strategic times over the course of a typical crop cycle. Therefore, the field crop surveys are conducted in March, June, July, November, and December, and are supplemented with the yield model estimates for July and September. The results help track major grain production nationally and provincially, indicate the availability of crops, provide annual trend information by crop and small area regions, and assist farmers in their planting and marketing. Like all statistical organizations worldwide, StatCan is under increasing pressure to reduce response burden and the cost of the traditional surveys while maintaining relevance, accuracy, timeliness, accessibility, interpretability, and coherence. Based on the criteria mentioned above, the objective was therefore to develop a robust crop yield model for the principal field crops of Canada. In order to do so, StatCan partnered with Agriculture and Agri-Food Canada, another federal department, and in 2014, AAFC provided a yield model that they had developed. Statistics Canada reviewed and modified the yield model to meet the agency's requirements and released the first set of yield estimates in parallel with the traditional survey results. Feedback from data users was very positive, and the 2016 September surveys was replaced with the yield model. As a result of the ongoing COVID pandemic, StatCan leveraged the knowledge gained in past modeling projects to meet the agency's goal through providing reliable statistics to Canadians without direct contact with respondents. Consequently, the July occasion of the crop reporting series was replaced with the crop yield model estimates. There are three primary data sets used in the yield model. The first is the Normalized Difference Vegetation Index, or NDVI. Canada is a large country geographically. The AVHRR and MODIS satellites record images of the entire Earth on a daily basis. Sensors on board these satellites capture these two spectral bands, red and near infrared, that have proven to be extremely useful for monitoring changing vegetation conditions. The NDVI values increase as plant canopies become more green and dense, but decrease as leaves come under water stress, become diseased, or die. The daily AVHRR satellite images are processed into weekly composites at StatCan, while AAFC processes the MODIS datasets and makes these available to the agency. An example of the NDVI composite is shown in this slide. Value-added products are produced using these weekly composites and distributed via the web in near real time. I would like to draw your attention to the fact that StatCan has the AVHRR data set from 1987 to present, a 35-year time series, and a 22-year time series for the MODIS data. Long time series are important in modeling crop yields. I have split the country into two parts, east and west, for ease of discussion. This slide focuses on Eastern Canada. First, let's look at the graph in the center. The y-axis shows the NDVI values, while the x-axis shows the date by Julian week. The blue line in the graph is the average, or the normal values of all the pixels from 1987 to 2020 for the selected region in the associated map, while the green line is the average of the 2021 NDVI values for the same selected region. The color assigned to each of these geographic regions is based on how far the 2021 NDVI values deviate from the normal. For ease of comparison, the legend contains 5 groupings from much higher through to much lower. These two maps show the same area, but they are about 5 weeks apart in time. Note that the crop conditions are similar to the normal over the 5-week period for the selected region, while the crop conditions in the southwestern portion of the map have deteriorated. The value-added product permits a quick and effective way to visualize the changing crop conditions throughout the growing season. This slide shows the same value-added product compared to the normal for the same date shown in the previous slide, but for Western Canada. Crop conditions for most of these regions were rated as higher to much higher than normal for the week of June 14 to 2021 or Julian week 24. Extremely high temperatures and below normal precipitation were experienced beginning the latter part of June. The map in the lower right corner of the slide shows the regional extent and severity of the NDVI decline over a 5-week period. These NDVI data by region are used as one of the predictors within the crop yield model. The high temperatures and minimal precipitation across Western Canada in 2021 negatively affected crop development. This slide shows a map where the maximum NDVI value for 2021 is compared to the maximum NDVI value for the normal. By comparing the peak of the two curves, it is evident as to when the 2021 NDVI peaked compared to the normal. 3 NDVI comparisons are shown, which indicate when the 2021 NDVI reached the peak growth. Center graph, 5 weeks or more ahead of normal. Lower left graph, 3 to 4 weeks ahead of normal. And lower right graph, 1 to 2 weeks ahead of normal. This was the first time since 1987 where the NDVI curves peaked in some parts of the country 5 weeks or more in advance of normal. The second data set used in the yield model is Agriclimatic Data. This map shows the distribution of the climate stations across the agricultural region highlighted in green. The station-based daily minimum and maximum temperature and precipitation data provided by Environment Canada and other partner institutions were reanalyzed by Agriculture and Agri-Food Canada to generate the climate-based predictors, which amongst others include cumulative precipitation, growing degree days, and a water stress index. Once in a format suitable for yield modeling, the data was transferred from AAFC to StatCan. The map on the left shows the departure from average precipitation in millimeters from April 1st to August 31st, 2021. This is the data that is used for the yield model estimates released in September. Large negative departures from average precipitation is evident for most of the agricultural region of Canada. The map on the right shows the number of days where temperatures were above 30 degrees Celsius. Most of Western Canada experienced prolonged periods of temperatures above 30 degrees. The concern expressed by many farm operators was that the current drought conditions hit at the worst time of crop development. In canola, for example, flowering can become heat stressed beyond 30 degrees Celsius, which can lead to small or aborted pods, fewer seeds per pod, and ultimately lower yields. The longer these abnormal conditions persist, the greater the negative impact was on crop and hay yields, grain quality, and ultimately farm cash receipts. This slide shows the water stress index for a single census ag region for Western and Eastern Canada from the beginning of May to end of August. The water stress index is calculated from the versatile soil moisture budget model, which is a one-dimensional water balance model that divides the soil columns into layers sharing common soil and plant root properties and calculates soil water balance on a daily time step. The water stress index effectively measures how close the rate of evapotranspiration is to the potential rate. The index ranges from 0 to 1 and is categorized into 4 groupings. Here you see the 4 groups with the severity of a water stress index ranging from 0, no stress, to 1, severe moisture stress. The 2 maps show the average water stress index by census ag region in Western Canada. The maps on the left, the combination of high heat and low precipitation led to extreme water stress on the plants. Eastern Canada was on average moderately stressed. Note that in Eastern Canada, there was a period from July 21st to August 21st where the water stress index was in the no stress to light stress zone. This occurred during the critical period of crop development, resulting in better yields than experienced in Western Canada, where the water stress index remained in the moderate to severe stress range during the entire growing season. The water stress index value by census ag region is one of the many predictors used in the crop yield model. Let's move on to the historical yield data and other predictors. The third data set used in the yield model is historical yields and is represented in the third column of the table. The historical yields are either from StatCan's November crop survey or crop insurance data. The November survey is late in the growing season when most, if not all, crops have been harvested, and the survey sample size is the largest of the crop reporting series. In short, it is the gold standard. Other administrative data sets, such as crop insurance data from the provincial crop insurance corporations, are also used if available. Only a few of the 80 predictors have been listed in this slide as an example. The current yield, yellow box, is calculated using the yield model. Crop yield can be influenced by a number of factors. Since yield can rarely be predicted by a single factor, a multivariate approach is more likely to provide more robust and accurate models. The yield model estimates are shown for July and September compared to StatCan's November survey estimate. A negative % difference indicates that the model underestimated the yield, while a positive difference indicates that the model overestimated the yield. The first general point is that the further the yield model estimates are from the November survey estimate, the greater the deviation. In 2021, this was not always the case, but was observed most often. Durum wheat and fall rye had the largest deviations from the November survey estimates. The September yield model estimates for dry field peas and flaxseed were 10.7 and 10.5% respectively. All the other September yield estimates had deviations that were between 3.3% to minus 6.4%, depending on the crop. Although the yield model had some deviation, especially in 2021 drought year, the grain industry representatives are very supportive of StatCan's yield model methods and results. I would like to use canola as an example in the next slide. Please note that the yield model estimates for canola was 17.1% higher than the November survey estimate, while the September yield model estimate was within 1.5% of the November survey estimate. Information is money. The left graph in this slide shows the 2021 NDVI curve, green, and the normal curve in blue. Early in the growing season, the 2021 conditions were below normal due to a late start in planting. Growing conditions thereafter were ideal, and the crops emerged and were very thick and lush from Julian week 22 to 26, indicating that the yield potential could be higher than normal. This was at the third week of June, indicated by the gray arrow. The price for canola at the same time was $740 Canadian per ton. Adverse weather conditions were experienced from Julian week 26 to the end of the growing season, as mentioned in the previous slide. The red arrow indicates the time when the September yield model estimates were released on September 14th. Canola prices were $860 per ton, which was a 16.2% increase from the third week of June. The last arrow In the price graph highlights the price of canola when the November survey estimates were released on December 3rd, Julian week 49. The price had risen to $1,022 Canadian per ton, or 18.8% increase from when the September survey yield model estimates were released. That means, excuse me, that means between the third week of June to December 3rd, the price of canola increased 31.8%. This emphasizes the importance of monitoring crop conditions using Earth observation in near real time and providing robust yield estimates earlier than traditional surveys can provide. In summary, the yield model uses 3 data sets: coarse resolution satellite imagery, agriclimatic data, and historical yield data. As a result of the ongoing partnership with Agriculture and Agri-Food Canada and provincial crop insurance agencies, the yield model replaced the September occasion of the StatCan crop reporting series beginning in 2016. The July occasion was replaced by the yield model in 2020. The benefits of using a model-based approach are similar accuracy between the model and survey-based yield estimates. July and September model estimates were released earlier than the traditional surveys, thereby providing the yield estimates to the data users earlier than previously. Reduced response burden, a cost reduction as the survey-based collection is no longer required for July and September occasions. StatCan is transitioning to the cloud for processing of satellite data. A secure cloud environment is being put in place to ensure the ongoing confidentiality of the yield estimates. StatCan and Agriculture and Agri-Food Canada continue to refine the model. I would like to emphasize the ongoing partnership between StatCan and AAFC, where the July and September release of the estimates is a joint release which may lead to one model for both departments. If you wish to contact me directly, you may do so using the email provided. Thank you.
Thank you, Gordon. If any of the participants have any questions, there's one question on the chat. Gordon, if you'd like to read that and maybe answer that, that'd be great.
The first question here is, what is the model that you use for forecasting the crop yields? And can the results decompose for each commodity? The yield model that we're using here is one that's been designed within SAS. We're transitioning to an R code format for that, but we haven't developed that quite yet. But the model has been developed and rigorously tested within the SAS environment. Can the results decompose for each of the commodities? There's certainly a variation or variability within the yield estimates compared to the historical data sets. And this is something that you will always encounter within a model. A model is a model and there are deviations. The second question, thanks for the link. Indeed, is the video related to Google Earth Engine will be shared? No, this is not a Google Earth Engine. We have been doing the processing in-house. We are looking at Google Earth and other options to do that. The rest of the question says, in addition, I wonder if the Earth Engine is publicly accessible or you need institutional contact to get granted an access. That's something I haven't looked into completely, although there is a large, there's certainly flexibility within Google Earth Engine for individuals, private companies, or NSOs to gain access. So I certainly would encourage anyone to look at the Google Earth Engine option.
Thank you, Gordon. I think we can move in with the next video that we have with Eduardo Vasquez, the Subdirector de Información Cartográfica. I'm not sure if I said that right. And then we have Ilio Villaseñor, the Director de Laboratorio de Ciencia de Datos. So please excuse my Latin. I'm not a Latin speaker. If you'd like to correct me, please go ahead. Ian raised, we have one person who wants to say something. Let's keep this for the end of the sessions in the interest of time.
Hi, are going to show you our presentation about. Hello everyone, my colleague Elio Villaseñor and I are going to show you our presentation about the development of an algorithm to produce the agricultural frontier using satellite images. I will present to you the first part of the presentation, in which I will tell you how was prepared the main input that was used at ground truth. First of all, I would like to comment on the definition of agricultural frontier used in this work. The agricultural frontier is the territorial distribution of the areas with agricultural activity, as well as the plots that were planted in the last 5 years, even if these do not currently have activity. This definition is based on the concepts of INEGI and Sept. Sept is an office under the Ministry of Agriculture. The main input is the information resulting from the 2007 agricultural census. Because of the census, individual plots and common use lands were digitized in a shapefile that integrates more than 7.4 million plots. For each plot, we have the attribute of the activity that develops in this. That is, if the plot is agricultural, livestock, or forestry. The main activity was updated in 2016 during the update of the Agricultural Census Frame, AMCA by its acronym in Spanish. We also include later updates derived from the conduct of the National Agricultural Surveys 2017 and 2019. Finally, between 2018 and 2019, we carry out a review with satellite images, in which the AMCA was compared with the agricultural frontier of Sept. And as a complement, the common use lands were also analyzed with satellite images to define more precisely the agricultural area inside. During the comparison of the AMCA with Sept's agricultural frontier, everything that coincided as agricultural area were considered part of the agricultural frontier. The areas that differed were verified with satellite image to update the AMCA. It's important to consider that the agricultural frontier and the AMCA are projects that were worked with different satellite images. The agricultural frontier was made using spot satellite images from 2015 and 2016, and the AMCA was realized with Sentinel-2 images from the years 2018 and 2019. In this slide, you can see the comparison of both inputs. It's clear the high coincidence. However, there are areas that do not match in both inputs. The review of the areas that did not match were done using coverage of Sentinel-2 images. It was also used Google Earth for some cases as support tool. It could be confirmed that some areas that the AMCA did not actually report agricultural activity did not have it. However, we also identified areas that where the AMCA did not report agricultural activity, but in the image there was evidence of this activity. This is one case. We also identify combined activity in some plots. On the other hand, in the review of the common use lands, which are generally very large lands, from 100 to 1,000 of hectares, in these common use areas, in addition to the identification of the agricultural activity, the agricultural areas were digitized in order to obtain the area of agricultural activity more precisely. we can see the digitized areas of agriculture. As a result of this activity, all AMCA plots were coded to identify those that are fully agricultural, as well as those that are at least 30% or more of their area has agricultural activity, and separate them from those that don't have this characteristic. Finally, with this codification, we obtained the data of the agricultural area of the country, obtaining just over 31 million hectares. These encoded plots are the input that was used in the training of the algorithm as ground truth. Well, I give the floor to my colleague Elio Villaseñor to continue with the second part of the presentation. Thank you.
Thank you, Eduardo. And now that my colleague Eduardo has told us how the AMCA dataset is constructed, I will tell you how we develop and apply the machine learning algorithm to obtain the agricultural frontier using remote sensing techniques. First, we take images from the Landsat geomedians provided by INEGI. The Landsat geomedians collection of INEGI was constructed using all the historical Landsat archives and the Open Data Cube framework to manage and process the images. This collection of 3 mosaics covers from 1984 to 2020, and each mosaic summarizes the national territory corresponding to a period of time, typically a year. The geomedian composing technique has the advantage of producing images free of clouds and shadows, and preserving the essential information of the satellite images. We use the 2019 geomedian mosaic to construct the training data set for this project. Considering the information provided by AMCA, we label each pixel of the Landsat geomedian image. The resulting labels were agricultural, mixed plus urban, and non-agricultural. At the end, for the training data set, we decide to take the mixed plus urban and the non-agricultural as the same class. By doing this, we convert our classification problem to a binarial one. And to perform the classification task at a national level, we have to consider it worthwhile to apply a no-supervised pixel classification technique for grouping spatially adjacent pixels. And by doing this, we reduce the number of objects and consequently the computational cost. We apply the clustering method called GeoIBIA, Geographic Object-Based Image Analysis, and obtain 9.1 million of clusters called clumps. This is a significant cost reduction considering that each Landsat geomedian national mosaic has 2.7 billion of pixels. By doing this mapping of the AMCA labels at the pixel level, we then label each clump by assuming that it belongs to the agricultural class if at least 80% of its pixels are agricultural and non-agricultural otherwise. Also, for each clump, we construct a multidimensional vector of 150 characteristics. extracted as a statistical measures from its bands. Finally, we consider a balanced sample of more than 500,000 elements and divide this sample into two sets, 80% for training and 20% for validation. We evaluate distinct machine learning algorithms to have a competitive baseline. Here, we can see the performance comparison between extra-trees and multi-layer perceptron. For the first iteration of the process, we find for finding the best possible classifier. To evaluate performance for the classifier, we calculate standard classification metrics like accuracy, precision, recall, and F1. Also, to understand the spatial distribution of hits and strikes, we map the confusion matrix for each clamp. We can appreciate the improvements we have reached by comparing the results from the first iteration with those from the fourth one. We can see that errors are not uniformly distributed. Red and yellow spots from the fourth iteration increase in the southeast side of the country. The last sentence is corroborated by analyzing the evaluation for each state. The worst performance are from those states of the country's southeast region. Another way to measure the performance of the classifier is by comparing the estimated agricultural area in each iteration with the actual one given by the AMCA dataset. One advantage of our pipeline and working with Landsat images is that we can use the obtained classifier to estimate the agricultural area from 1929 to 2021 and analyze the trend of this estimation. Here, we show the results for this estimation for each year. Now, we are working on applying the exposed pipeline for the classification of Sentinel images. The results so far show a promising improvement of the accuracy already obtained. Also, to increase the performance, we are working on the construction of an ensemble that considers local classifiers. Finally, depending on the precision, we will evaluate the usefulness of the results for the continuous update of the agricultural sample framework and the collected information control. Thank you very much.
Thank you. Thank you, Elio and Eduardo. Very insightful indeed. We're at the end of our presentations, and I would like to thank you all for joining. If anybody has any questions, please feel free to ask them.